Hello friends, so today we are going to look at application of the Vsepr theory in predicting molecular geometries. Recall in the last video we introduced the Vsepr theory and how we use it and how it applies in trying to explain or describe the geometries and shapes of molecules. Okay, so the Vsepr model ultimately can be used to predict the shapes and of course the geometries of different molecular species, so long they have a coordination number, or what we call the steric number, ranging from 2 to 7. Okay, what we are trying to say is that once you have 2 or more atoms attached to the central atom, we can use the Vsepr theory to determine what we call the molecular geometry of that molecule, okay, or molecular ion. That's why we say molecular species, because we could be dealing with organic molecules, inorganic molecule, or molecular ions. That's why we say molecular species. So when you are dealing with molecular species that have 2 to 7 electron groups or electron pair domains around the central atom, of course, the Vsepr theory is suitable and becomes convenient for us to use in describing the geometry of those molecular species. Nice. So Ronald Gillespie and Ronald Naulum, of course, described structures of molecules to be in the form of what we call AXN. Of course, where A represents the centrally placed atom, and of course the X represents the terminal atoms, or what we call the N number of terminal atoms. Okay, so of course the small n represents the number of those atoms that surround those X atoms, or those terminal atoms that surround the A atom, which is the centrally placed atom. Nice. So there are different molecular geometries that we must pay attention to, but for the purpose of this particular lecture, I'm going to pay attention to just 2. In the next lecture video, we're going to move up to higher ones, and then we get to the more advanced ones. So for today, we are going to briefly look at the linear molecular geometry and of course the trigonal planar geometries. First, the linear geometry. When you talk about the linear geometry, you see that its Vsepr form is in AX2. Of course, from this generic formula, we have AX2. What that means is that we have 2 atoms attached to the central atom A. So we have 2 X atoms attached to the central atom A. All right? Here, because of the 2 atoms attached, you say that it has a steric number of 2 or has a coordination number of 2. When you are talking about steric number, you're talking about the number of atoms or lone pairs of electrons that are bonded to a central atom. In this case, we don't have lone pairs of electrons, we only have 2 atoms attached to the central A atom. That way we say that this has a coordination number of 2 or steric number of 2. All right, so this AX2 molecule has a generic formula given us, of course, you have your centrally placed A bonded to the left to an X and bonded to the right with another X. That is why X is 2. So we have 2 terminal X atoms and A centrally placed. So when you have this kind of model of format, AX2 format, 2 terminal atoms attached to a centrally placed atom without any lone pair of electron around there, you are going to make what we call a linear molecule. And linear geometry is found in molecules such as beryllium chloride, carbon 4 oxide, hydrogen cyanide, and so on and so forth. Remember again, when you are talking about Vsepr theory and shapes of molecules, we treat single, double, triple covalent bond as though all of them represent 1 electron domain. All right, nice. So for beryllium chloride, of course, this is the Lewis structure of beryllium chloride. Again, recall that beryllium chloride is one of those molecules that are called electron deficient molecules. Those molecules that has valence electrons of beryllium not up to 8. However, they are still stable and okay with it because they are exceptions to the octet. So with this said, you see that beryllium is bonded to this chlorine by one covalent bond and to the other chlorine by one covalent bond. So you have 2, 4 electrons, and beryllium is satisfied or stable that way. Nice. But one thing you need to understand here is that had it been we have a lone pair of electron on beryllium, what happens is that this is an electron domain with an electron cloud. Of course, this is an electron domain with bonded pair of electron, and this is a bonded pair electron domain. So this will now be negatively charged, it will be negatively charged, this will be negatively charged. So these 3 bonds will try to repel each other according to the valence shell electron pair repulsion. They will try to move away from each other. That way, this bond would have been slanted and not this linear. But because we don't have any lone pair of electron on the centrally placed atom, remember it is the electron domains on the central atom that determines the geometry of a molecule. So had it been we had a lone pair of electron here, this angle will not be in a straight line because these 2 bonds would have slanted or moved downwards, creating a different kind of geometry away from this straight geometry that we have. Okay, so because this molecule is in this straight form, you say that angle on a straight line is 180 degrees, and such a molecule that has 180-degree bond angle, okay, is known as a linear molecule. So it's not only in beryllium chloride that you find this kind of linearity in geometry. You also find it in molecules like carbon 4 oxide. Again, carbon 4 oxide had no lone pairs of electron. Had it been it had a lone pair of electron, there would be again repulsion, and the angle will not be on a straight line the way it is. The bond angle will not be on a straight line. So ultimately, you discover that the bond angle again is 180 degrees, and of course, again, you have a linear molecule. Again, you find that in hydrogen cyanide. Again, you have the difference between this electron domain and this electron domain being a straight line angle of 180 degrees. Remember, we are not we treat triple and double bonds as if they were a single super pair, or as though they are single covalent bond, or they represent one electron domain, one electron domain, one electron domain. All right, so this is very, very key that we understand it. So you can now agree with me that molecules with linear geometries have 2 coordination of steric numbers, or 2 atoms attached to them, to their central atom, of course, with no lone pairs of electrons on that central atom. In other words, we can as well say that the Vsepr format for molecules like this is AX2E0. We're now bringing in the third variable here, which is E. Of course, E represents lone pairs of electrons. So when we say E0, what we're trying to say means we don't have any lone pair of electrons. So we say E0 is 0 lone pairs of electrons. So this particular AX2 that we find in linear molecules can as well be this can be written in an expanded format of AX2E0. Okay, so of course the A represents again the centrally placed atom, the X2 represents the terminal atoms, the E0 represents what? That there is no, the E represents lone pairs of electrons. So E0 means there is no lone pair of electrons. As we proceed, you're going to see some Vsepr formats where you have E1, it means one lone pair of electron. You're going to also get to a point where we have AX2, whatever, and E2, trying to tell us that on that molecule we have, in the central atom of the molecule, we have 2 lone pairs of electrons, and so on and so forth. So simply, linear molecules has 2 electron domains or atoms bonded to the central atom. Of of course, with no or zero lone pairs of what? Electron. That is why, summarily, we can say that their Vsepr format is AX2E0. Nice. So the next kind of molecular geometry we're going to explain right now is the trigonal planar geometry or molecular geometry. Of course, here it shows that the Vsepr form is AX3. All right. So we are now talking about molecules with 3 coordination or steric number, or what we call 3 electron pair domains. So we're expecting 3 covalent bonds to go out of the central atom, of course, to link up what we call the terminal atoms. So we have AX3 generic format here, okay? Of course, this is the generic formula. This is what we call the generic, okay, or general formula. Generic or general formula. Because you see the centrally placed atom with 3 terminal atoms around it. Nice. So examples of this geometry, you find it in molecules like boron trifluoride, BF3, and you also see it in formaldehyde molecule, CH2O molecule. So this, of course, represents the Lewis structure or diagram of boron trifluoride. Again, you see Lewis structures shows us molecules, the structures of molecules in 2 dimensions. But in reality, we live in a 3-dimensional world. So the Vsepr theory helps us to now see the way the electron repulsion pair, that interaction between them helps us to create the different bond angles between the covalent bonds present. And of course, ultimately, we can be able to predict the molecular geometry. So this is an electron domain, this is an electron domain, this is an electron domain. The 3 of them represents negative electron clouds. So as a matter of fact, these 3 bonds we want to stay away from each other as far as possible, according to Vsepr theory. So there will be some repulsive interaction between this bond and this bond. So these 2 bonds below, these 2 bonds will try to move away from the initial or the first covalent bond here. That way, we're going to have a bond angle of 120 degrees, just like you have in a triangle. Okay? Nice. So this particular kind of molecular geometry is known as trigonal planar shape or geometry. Again, the generic format is what? AX3. So when you have 3 things surrounding a central atom without any lone pair of electron, definitely what you have there is called trigonal planar shape or geometry. This is also seen in the formaldehyde molecule. Okay, again, remember here we treat double covalent bonds as a single super pair. So in this particular Vsepr model, we are looking at this as a single super pair. So we are looking at it as just 1 electron domain. All right, nice. That way again, these 2 covalent bonds, of course, makes that bond angle that is 120 degrees, just like what you see whenever you have a centrally placed atom with 3 atoms surrounding it and no lone pair on the central atom. Had it been there's a lone pair on this central atom, the geometry would have been a different geometry. Beautiful. So again, in summary, you can now say that molecules with 3 steric number and no lone pairs on the central atom has a trigonal planar geometry. Again, we can decide to write the Vsepr format in the trigonal planar molecule again as AX3E0. Of course, E0 here shows us that we don't have any lone pairs of electron on the centrally placed atom. In the next video, in the next lecture, I'm going to take it to the next level and we talk about other kind of molecular geometries till we get to the very advanced ones, so that you keep learning and keep bettering your chemistry. I remain your friend, Dr. Lotan Nokwesili. And until the next time, keep enjoying chemistry, keep being safe, and stay away from trouble. Okay? Bye.